All right, so since we've been looking at two data sets recently, we're going to talk about something called correlation. So correlation is a relationship between two variables. So we can think of this as ordering the data from each variable into ordered pairs, so an X and a Y. Here, we're talking about trying to get some link between these two variables. So X is going to be the independent or explanatory variable, and Y is the dependent or response variable. So X is the thing that we're trying to maybe establish as explaining why something is happening, and Y is the response, the thing happening, and we're trying to measure that based on the X. So if we look at a scatter plot, which we've looked at before, that's just graphing out all these ordered pairs to get a picture of it, where we put the independent or explanatory variable X on the horizontal and the dependent or response variable Y on the vertical. And the scatter plot is a way that we can see whether a correlation exists between these two variables. The correlation that we're going to be looking for is a linear straight line correlation, although there are other types of correlation, but we're going to be focusing on linear correlation. And then in the next section, we're going to be looking at linear regression. So let's take a look at this as some of the pictures that we would get here if we plotted these out in a scatter plot. So what we're seeing here in this first picture here is what we'd call a negative linear correlation. In other words, that it kind of looks like a line sloped downward. So hence negative meaning that as the X increases, the Y values decrease. All right. The other way would be a positive linear correlation, which meaning as X increases, Y also increases. Now, in this example here, we don't see any correlation. There's really no structure to the points that are being plotted there. While in this last one, we do see a correlation, but it doesn't appear to be linear. All right, there appears to be maybe a parabola that we could fit that, so there may be some sort of quadratic correlation, but that's something that we're not going to look at right now. So let's take a look at an example of some data. So let's say we wanted to construct the scatter plot here to determine whether there's a linear relationship between a country's gross domestic product, GDP, and the carbon dioxide emissions. So we have the data for a bunch of countries here, each with its gross domestic product and its carbon emissions. And so these things are going to be the XY coordinates that we would plot. So there's the plot, and we see that we have the GDPs here and the emissions over here. So each of these, so this point right here, this GDP here of about 4, giving something in the 700s for the emissions, would correspond to right here, the 3.9, 742.3. But what we're really trying to do is look at the whole thing all together and determine if there's some structure. So it does appear that there's some evidence that we have that as X increases, Y increases. So it looks like we have some sort of positive linear correlation. And we could seem to say, well, the graph suggests that as the gross domestic product increase, the carbon dioxide emissions tend to increase as well. But obviously, we're going to want to quantify this in some way. So we have what's known as the correlation coefficient, R. This is a measure of the strength and direction of the linear relationship between two variables. How strong do they make a linear relationship? And is it a positive relationship or a negative relationship? So that's why we use R. And this is the sample correlation coefficient, assuming that we're taking this out of samples. And this is the quite involved formula for R. Well, I'm going to show you what goes into calculating that by hand. That is not something we calculate by hand. That is something that we use technology to do. So that sample correlation coefficient is the correlation between these two populations that we are approximating by this sample correlation coefficient. The population correlation coefficient is rho. So this is the Greek letter rho. So that's the thing that we're using R as a test statistic for. So it's important to notice that there are only a certain range of values of R, and that's from -1 to 1. So at -1, an R of -1 would mean there's a perfect negative correlation. So these things would line up in some negatively sloped line perfectly. You don't usually get that, but that's how it would appear for R equals -1. For R equals 0, there's no correlation evident between these two variables. And R equals 1 is a perfect positive correlation, meaning it would be some positively sloped line, lined up exactly along the line. So that's, again, unusual. But so what we usually are doing is seeing values somewhere, inside here. And that's what we're trying to determine for two sets of data. So what we can say is that the positive or negative nature of the R tells whether it's going more towards a negative correlation or a positive correlation. And then the size of the absolute value of the number tells how strong the correlation is. So if that absolute value is close to 1, it's strong. And then if the number itself is negative, it would be negative. And if it's a positive, it would be positive correlation, as in some of these graphs here. So again, this one is a perfect positive correlation because they line up in a line. This one is a strong positive correlation because they are showing trending upward as x increases, and they're fairly well grouped. So that, well, we can't measure that from this, but let's say that's an R of 0.81. Here, they are trending upwards, but they're a little scattered out about that trend line there. So it is still seem to be a positive correlation, but it's a weak positive correlation as opposed to that one, which was strong. On the other end, so this is perfectly in a line with a negative slope. That's the perfect R equals -1. This is somewhat tightly grouped around a negatively sloped line, hence a strong but negative correlation, and you can see that number in absolute value is 0.92, which is close to 1, indicating the strength of it. And here, an R of 0.04, very much close to 0, shows no correlation between the two. There doesn't seem to be any connection. So again, it is a very complicated calculation if you were to do it by hand. So if we go back to this data here, let's see what the calculation is, but more importantly, let's see what our conclusion we can make out of this. All right, so you would have to do all these things if you were to do it by hand. You get the sum of the x values, the sum of the y values, the sum of x times y for each case, the sum of x squared for each case, the sum of y squared for each case. And then you put that into this mess of a calculation here, a lot of craziness, and then we get this 0.874. So an R of about 0.874 suggests a strong, because in absolute value it's close to 1, it's big in terms of going towards 1, and positive because it's a positive value. So a strong positive linear correlation, again, what it's indicating is that as the gross domestic product increases, the carbon dioxide emissions tend to increase in a strongly positive correlation.